Next, we're going to look at an object that is being pulled upwards, and this time it's accelerating at 2 meters per second squared. And so now I do have a net force. If I didn't, then I wouldn't have acceleration. A free body diagram has tension acting upwards and gravity acting downwards, but the tension force is a little bit larger than the gravity force, which is why it's accelerating upwards. I write my free body diagram equation again. I have Ft acting upwards. I won't put the positive sign here, I don't need to. Minus Fg is equal to some mass times acceleration. And so then if I write down my equation, Ft minus Fg is equal to the mass times acceleration, so Ft would equal to ma plus Fg, which is going to equal to 3 times 2 plus my force of gravity, which was again 3 times 9.8. And then that gives me 6 plus 29.6, which gives me 35.6 newtons. So you notice that the tension increases on the string as it is accelerated upwards. Now you could take a mass on a string and do this yourself. Pull it upwards and speed up as you're pulling it, and you should feel the mass feel heavier on your finger than if you were just bringing it up at constant speed or just holding it in one place. Let's look at the same thing now, where this mass is still hanging by an object, but it is accelerating downwards at 2 meters per second squared. Again, I make my free body diagram. Tension is the only force acting upwards, and gravity is acting downwards. But this time, my force of tension is smaller than my force of gravity. I'll just make this a little bit longer. And so that's what my free body diagram looks like. Clearly, there's acceleration downwards as the force downwards is greater than the force upwards. If I write my free body diagram again, the equation for my free body diagram, and again, that's why we make these free body diagrams, so that we can then use Newton's second law and make an equation. Again, recall that Newton's second law is the sum of the forces is equal to mass times acceleration. And so if I do the same thing here, tension acting upwards minus the force of gravity acting downwards, and that is equal to my mass times acceleration, but this time my acceleration is downwards, so I put a negative sign up there to show the direction of the acceleration. So now Ft is equal to Fg minus Ma, which is 29.6 newtons. That was my force of gravity from up here, minus 2 times, or rather 3 times 2. So that becomes 29.6 minus 6 newtons, and that gives me 23.6 newtons. So now we notice that accelerating it upwards increases the tension, when accelerating it downwards, I'm sorry, you didn't see all of this writing that I did up here. And so that tells you that the tension is lower when it's being let down while it is accelerating, and the tension is greater when the acceleration is upward. So upward acceleration increases the tension. The downward acceleration decreases the tension. What we can see from here is, again, if you were to do this manually and take a mass and kind of let it down really fast, you'd find that the tension in the string becomes less. And you could feel that on your finger as well if you just wanted to get a feel, an intuitive feel for the force of tension. And so if you really wanted to look at it upwards, you would see that when you are accelerating it upwards, you could literally write down that the force of tension would be m times g plus a, which is what we did up here. It doesn't look necessarily the same way that I wrote it down here, but you can see that if I were to take the mass and pull it out as a common factor, I would just get g plus a. And then the force of tension when it's being released downwards will just be m times g minus a. So that's a convenient way to remember these and be able to figure out the tension on your string as it's being lowered or made to go upwards. Okay, so that is a basic wrap-up of tension on a string when something is being pulled upwards or let downwards with acceleration.